So let's get started. So today it's a new event in a sense. So it's a collaboration between the Game Theory Center and Sola Center at University of M6P. And we have the big pleasure to have Suresh Sethi, Professor Suresh Sethi. So he is Eugene McDermott Professor of Operations Management at University of Texas, Dallas, and Director of the Center for Intelligent Supply Networks. So he got his PhD before I was born at Carnegie Mellon University in Industrial Administration, and he did a postdoc at Stanford with nothing less than George Danzig, one of the great mathematicians and mathematical programming guy. So lots of respect for this guy, but so let's talk about our speaker. So he has lots of publications, top-level publications, 7 books, 400 research papers in many fields, including manufacturing and operations management, finance and economics, marketing, and optimization theory. He was editorial board in many journals, including Production and Operation Management and Science Journal on Control and Optimization. And he's fellow of the Royal Society of Canada, fellow, Informs Fellow, AAAS Fellow, POMS Fellow, SIAM Fellow, but also past president of Production and Operations Management Society. So, just to say, Suresh is an amazing, productive scholar, and I am very honored to have him here at Morocco, in Rabat. And I'm also very excited to see game theory applicable in real life. And since we are very interested at University of M6P by operations management and supply chain and all these kinds of things, I am very excited to see how I can apply what I learned theoretically to real world. So, Suresh.
Thank you, Rita. Thank you for inviting me. How do I start? Since you told me okay. So it's been more than 35 years since I last came to Morocco. Morocco is totally different. It's all built up. I see quite a bit of energy here. 35 years ago, it was a kind of an old country with things that we like to see, like old Medina and things like this. Since then, actually, I've been to maybe more than 100 countries. And so I'm coming back to Morocco and pleasantly surprised. I am here to give a keynote speech in Marrakesh in combinatorics. And so decided to also visit a few places, and it's been so far wonderful. Okay, so what I'm talking about are 2 things. There is what is called a supply chain coordination in our field, and I'm going to begin with that and why I started working on this problem. I think I have to go this way or this way. Does it matter? Yeah. So let's begin with where I begin. Invariably, there's a conflict in supply chain. How does that come out? The supplier sets the wholesale price, and the retailer sets the order quantity. The supplier sets the wholesale price to maximize his profit, and retailer responds to that wholesale price and decides on an order quantity. So if the wholesale price is high, order quantity will be low. If it's low, the order quantity will be high. That's called a reaction function. So what you see is the order quantity is a function of the wholesale price. But their self-serving action do not maximize the profit of the supply chain. The profit of the supply chain means the profit of the supplier plus the profit of the retailer. And the reason is called what we in our field call double marginalization. And why? Because supplier puts up a margin over his cost, to set the wholesale price. And the retailer then earns a margin that equals the difference between the retail price and the wholesale price. And this particular problem is modeled as a Stackelberg game. That means there's a leader-follower game, also called a hierarchical game. Okay. Then we get into a Stackelberg equilibrium. We want to discuss the popular Nash equilibrium, whom you might know from the movie Beautiful Mind. So I'm going to play that clip soon. So in a game of 2 or more players, a set of decisions by the player is a Nash equilibrium. If no player can do better by changing their decision or his decision while the others stay with the decision. Let me look at this way. Okay. If a player can do better by changing his decision, knowing that decisions of others are set in stone, then it is not a Nash equilibrium. So let's review this particular situation in this movie. So I'm sure you've seen all this movie before, but the subtitles do help. It gives you a little bit more of insight of what's going on. So in the movie, Nash thanks the blonde woman for his epiphany and goes home to write his 26-page thesis, which is called the non-cooperative games, where he develops the concept of Nash equilibrium. 4 friends, I suppose, act on Nash's advice, and they all choose brunette women. And the question, of course, is do the decision form a Nash equilibrium? Anyone for yes or no? Well, it doesn't, because it's not a Nash equilibrium since each friend could gain by going for the blonde woman while the others stay with the brunette woman. So they can, and so by our second definition, it's not a Nash equilibrium. Okay. There's also another thing I want to say is that if you see how, at least in the movie, how the idea develops, he starts with Adam Smith needs a revision. Then he says Adam Smith is incomplete, and finally he said Adam Smith is wrong. So it is very fast development, and that's what we call epiphany. And he thanks the blonde for that idea. Okay, I want to do this because I want to contrast that with the Stackelberg equilibrium. That's the reason I start with this. And I'm going to give you the same example now, and I will see how the Stackelberg equilibrium is different than that. So I simplify the game by only 2 players, which is Tom and Dick. And I have 2 women. I was doing blonde and brunette, but my daughter says, no, that's not politically correct. And so I decided to change their name from Emily and Linda. Both men prefer Emily to Linda. No one gets any if they both choose the same girl. So now you can see there are 2 Nash equilibria here. Tom chooses Emily, Dick chooses Linda. Tom chooses Linda, Dick chooses Emily. There are 2 Nash equilibria here. And you can see in the first one, if Tom deviates by going for Linda, he suffers by getting none. Likewise, if Dick deviates by going for Emily, he suffers the same fate. Similar argument holds for 2. So we have a 2 Nash equilibria. No one has a first mover advantage here, but you will see the next thing. Now we're going to go and start with the Stackelberg equilibrium. By the way, incidentally, Stackelberg wrote his thesis in the book Market Structure and Equilibrium in 1934. And you know the famous tome by John von Neumann actually came in 1944. I happen to know some people. My advisor wrote a book with Morgenstern, Jerry Thompson. So I know a little bit of the story about this. But anyway, you must also admit that there is a book by von Neumann in German. It was published in 1928. So what von Neumann and Morgenstern do is what's called a zero-sum games. So zero-sum game, and they developed that major theory for that. And then comes Stackelberg, who develops the leader-follower game. And then finally, we have a Nash, who goes and generalizes the zero-sum game to Nash game. So that is a little quick primer on game theory. So let's now look at the Stackelberg equilibrium. So when I gave this talk, I gave the talk to a general audience, so I decided to have as little equations as possible. Later on, of course, I will change that, but this can be done mathematically, but I'm just doing it graphically or by a table. So you can see now the sequential game is played backward. So first what we do is we obtain the best response function or Dick for every decision that Tom makes. So the response function or decision is a function of the decision that Tom makes. Okay, the function is given here as a table. So here this one doesn't work here, right? So let me just go through this. So function of Emily is Linda. Function of Linda is Emily. That's the reaction function. So you can see there are 4 reaction functions here: purple, yellow, blue, and gray. Now, so what happens is that Dick's 4 possible functions are shown in purple, yellow, blue, and gray, and purple is his best response function. So what happens is, given the Tom's decision, his best decision is purple. Okay. And then what happens is, once the Dick's best response function is known, that is taken into account by Tom. So the Tom's problem then becomes a problem just to choose the girl, given the purple response function, and he chooses Emily, and then this function, when he chooses Emily, the response function says you that Dick chooses Linda. So you notice here, first of all, there is a first mover advantage here, because Tom gets Emily. Emily is the preferred woman here. However, here we want to say something which is different. Tom deviates, he loses, given the best response function for Dick and purple. So we are not saying that Tom deviates, he loses, given what is chosen by Dick. Dick doesn't choose a girl. Dick chooses a response function. That is it's an important distinction between Nash and Stackelberg. If Dick changes his response to yellow, blue, or gray, given that Tom has chosen Emily, Dick loses, it stay the same. So in some way, it is similar to Nash, but the space of deviations for Dick changes. It changes from the girl to the response function. So the obvious difference is that Nash involves simultaneous decision, Stackelberg has a hierarchical sequential decision. Also clear that Tom has the first mover advantage in Stackelberg because he gets Emily. Subtle difference is that Dick's deviation for changing the Nash equilibrium is to change his action going from the woman in the equilibrium to another, whereas the deviation approaching the Stackelberg equilibrium is to change his response function going from purple to another color. So that is a big difference. And so that difference will give us the definition. What I'm getting at here, I'm trying to develop the dynamic version of these ideas, because the supply chain coordination that was done before this paper was single period supply chain coordination. So I'm trying to develop how to do the supply chain coordination with multiple periods. We'll talk about that later. There's another less well-known difference when it comes to dynamic games, and I'll discuss that in slide 24. So before let's go, let me go into the idea of supply chain. So when we notice that there is a double marginalization when you do supply chain, then how do you deal with removing that double marginalization? The way it is done is what is called supply chain coordination. That means the leader gives a contract, and the follower would accept or reject the contract. But once the contract is signed by both people, then the contract results in the first best profit, which means if the two companies were together acting as one company, there was not going to be any double marginalization. The profit will be larger in most cases. And so we want to achieve that larger profit. And once achieves the larger profit, the difference that you create is split by the two parties in some way or another, which we don't address how they split the difference because they get into a bargaining issue. But what we have done in a supply chain coordination is a contract that achieves the first best. Go ahead. The one that I gave you is a wholesale price, but the buyback contract is equivalent to wholesale price contract. There are many different contracts. So you want me to explain buyback contract also? Yeah, but the wholesale price contract and the buyback, this is called revenue sharing contract and buyback contract, they are kind of equal. But I'm not going to go through the contracts. I'm just trying to tell you that the first best coordination is given by only for single period. And there's a lot of literature on single period, different kind of contracts and all that. So how do you go from one period to two period? You need to generalize the Stackelberg for one period to the second period. Remember, Nash was generalized long time ago, but the Stackelberg equilibrium was not generalized to dynamic setting for quite some time. Bassar Olser book has some ideas about that as well. Okay, sorry, a little bit, didn't get enough sleep last night, but anyway. Okay, so one of the things that comes when you generalize from single period to multi-period is to type of solution. In a single period game, there's only one kind of solution. In the multiple period games, there may be many different ways to solve the problem. One possible way is what's called an open loop solution. What happens in an open loop solution? Supplier announces the wholesale price in period 1 and 2 together. Open loop solution means all decisions are made at time 0, at the beginning, time 1 if you want to call it 1 and 2. So all decisions are made in the beginning. So the supplier or wholesaler decides price 1 and price in the wholesale price in period 1 and 2 at the beginning of the game. Yes?
You can announce the price of period 2 contingent of what happens after period 1. And in that case, it will be...
But that's not open loop.
It's not open loop.
Yeah, but I'm going to go to the... Well, we're going to go to the next game.
You don't condition in the open loop. In the open loop, you don't condition
No, no, no. You don't condition anything. Yeah. The best response function then would be the prices, the quantities, but the quantities now in period 1 and 2 will be function of P1 and P2. Like the P1 and P2 will be the price, the quantity will be a function of P2. That means even the first period quantity will depend on what happened in period 2 price, okay? And the leader continues to have the first mover advantage because the open loop problem mathematically is a single period problem. So P1, P2, Q1, Q2 are just a vector instead of, there's no time associated with them. It's not like Q2 goes before Q1 or Q2 comes after Q1. There's no such time. The drawback is the solution does not take into account the realization of demand in period 1 because demand is stochastic. And whatever it happens, nobody takes into account the demand. So it is not a very good solution. But people do open loop because it is sometimes that is the only way we can solve the problem. Go ahead.
So we say analysis, there is no commitment. And that's why there is this type of consistency, I guess.
That is true, but without full commitment, the problem doesn't get solved. So you have to have a full commitment.
So here it's full commitment.
It's a full commitment. It's a full commitment because that's the only way. Because otherwise, supply has an incentive to period renege on the wholesale price announced for period 2. So in order for you to make any justification of this game, you have to have a full commitment. Now let's see, since it's a game theory center, here's an open problem. Suppose there is no full commitment. Okay? Then the supplier has an incentive to renege if the demand realization happen to be such that the supplier will gain by changing his decision. Right? So now the question is, what are the penalties of changing the decision? Remember now, even though the commitment is full, who is going to guarantee the commitment? In our field and in economics, they say court will guarantee. But the court cannot guarantee. Suppose by changing my decision, I make $1 million more. Suppose the maximum penalty is $500,000. Then I will change my decision. So the one open question is, bring in a court and bring a finite penalty, because infinite penalty does not exist in our societies. The infinite penalty will be a death sentence. For civil crime like that, nobody will give you a death sentence, or it will be an indentured slave for the rest of your life. That's illegal. So the penalty has to be finite. Now the question is, how do you work in a finite penalty in this game? So far, I don't know any paper. No paper exists in which the commitment is partial. Commitment has a penalty. And then how do you solve this game? Okay? So economics, most of the economics you will see, what we do now is what is mathematically expedient. What we cannot solve, we leave it to somebody else. Sometimes it never gets solved. So that's the problem. So I am proposing a different solution here. I'm proposing a feedback Stackelberg solution. So by the way, I just want to make a little remark here. If you look at the mechanism design, what is going on here? Yeah. If you look at the mechanism design, Meyerson's revelation principle only holds for single period. And it will hold for open loop. But it will not hold for feedback. And so we do not have mechanism design with the feedback solutions because it simply doesn't hold. So once you do not commit yourself to only truth-telling solutions, then everything becomes complicated. So okay, so here's the feedback solution. Supplier announces only the first period wholesale price at the beginning of period 1, and then a solution in period 1 must anticipate what would happen in period 2. So that is what is going on. In period 2, the supplier announces the second period wholesale price after observing the inventory in the first period. The inventory means the demand realizes, you have some order quantity, you subtract the demand from the order quantity, you know what the inventory is. It's either 0, or if you allow backlog, it's negative or positive. So whatever the inventory is, the retailer responds to the supplier's wholesale price period-wise to obtain his period-wise order quantity. Both take into account the state observed in the second period. Solution is time consistent because you solve it backward. And what is the time consistent? Time consistent means that if you solve a dynamic problem at time 1, And if you have a feedback decision all the way to multi-period period on, let's say, time t. If you resolve the problem at any other time, let's say time 3, the solution is not going to change. But in open loop, the solution is going to change because that's what the commitment is required for. But here, the solution will stay, so it's time consistent. So that issue is not there. However, there's a drawback. The leader only has a period-wise first mover advantage, not a global over time first period advantage. Go ahead.
So here the supplier observes demand also?
See, everybody observes. It's a full information. This is not an asymmetric information problem. We are not getting there today. I just made that remark as an aside. But all of it is a full information game.
What about the from the retailer not to deviate from the best response?
Retailer to deviate? Because retailer has the best response function.
Yeah,
So your question is good, but let me mention to you what's going on. My aim here is to find you a coordinating contract. I will find a coordinating contract for the two-period problem. So once you find a coordinating contract, you get the first best solution, and nobody would deviate from whatever they want to do. Because under the contract, I will coordinate the supply chain. Okay? So this is the idea. The idea is, if you can coordinate the supply chain, why bother, right? So this is my pitch on this particular situation. So here is a application to this particular methodology. And that paper is actually published in 2015, but I'm producing it anyway here because I create now a two-period problem. I don't create the news vendor problem, as you know. I create a slightly different problem. And part of the reason is that the news vendor problem has been around for a long time, and people never looked at it. And either they never looked at it because they did not know how to deal with the Stackelberg equilibrium for multi-period, or they didn't look at it because there is no closed form solution. In our field, a lot of papers get published because there are explicit solutions. Okay, so I've created a different problem which has a closed form solution. It is a stochastic problem. It's a two-period problem, and I find a coordinating contract. So let's just look at that. So what I do here is that the cost of production in the second period depends on how much you produce in the first period. Such a thing is called cost learning. Arrow has paper on learning by doing, Kenneth Arrow. So there's a lot of literature on how you learn. And so I don't want to get into that, but here's what I'm going to do. Learning curve is learning by doing. It's called the experience curve. The earliest paper that we know, which is by Wright, 1936, it says direct labor cost of manufacturing airframe fell by 20% with every doubling of the production. So when you double your production, you learn more, and you learn to reduce the cost of production for the next aeroplane frame. I do want to say that every time I present this paper, they think this is the Wright brothers, but this is not the Wright brothers. That's a guy who flew the Kitty Hawk plane, and the Kitty Hawk is not this guy, but he's a different person. There are a lot of reasons for learning curve: labor efficiency, less time in discovering the manufacturing problems, all of that, better use of equipment. I'm not getting into that because there's a huge amount of literature on that. What I need in my problem is learning effect is dynamic and stochastic. So the cost falls with the cumulative production over time. Empirically, the rate at which the cost decline is vary widely both across and within industries, and even across departments within a firm. Particularly true for a production of a new product, there will be uncertainty. For example, when the semiconductor manufacturing was new, there was a lot of uncertainty in the cost of production. So let's begin with how to optimize in the process of learning. Did I miss a slide here? Yeah, okay, let's go. So first, we look at the centralized problem, which sets up the benchmark, because this is where we make the most profit. So in a centralized problem, the retailer and the manufacturer are the same company. and they know that they're going to learn. So when they're going to learn, what they can do, generally speaking, they will reduce the price in the beginning, in the first period, because when you produce, the demand is price dependent in our model here. So when you reduce the price, people will demand more. And when you demand more, you produce more. When you produce more, you learn more. When you learn more, you have a lower cost in the second period production. So overall you benefit. So by lowering the price, you benefit. So the optimal production quantity overproduced initially. Optimal price, what is optimal price? And so you can have a reduced price to increase the demand, resulting in increased production, greater learning, lower future production costs. And so the problem is manufacturer decides price and production. It's a dynamic programming problem. And dynamic programming problem is solved it backward from period 2, and you get your optimal profit. Now what happens? In a decentralized situation, manufacturer sells through a retailer, and the retailer has a pricing power. So the retailer will set the retail price. Okay? Higher price and suboptimal production, because learning curve effect may not be fully realized. It turns out that in the news vendor problem that you talked about, and also in this problem, without the coordination, it turns out that the retailer charges high price in the first period. And that is the reason, that's why people do revenue sharing or buyback price. Because the retailer charges high price because the retailer thinks that if the demand is not sufficient, he will get stuck with the products. So he orders less because the price is higher. He orders less wholesale price, and then what happens is, so what do the manufacturer says? He says I will share your revenue. So that is a percentage of revenue, and that will make the retailer order more, or also price should be lower. Or you can have a buyback price. You can say, okay, whatever you don't sell, I will buy back at a certain price. Either way, you can coordinate the supply chain. So we know that even without cost learning, the double marginalization exists, and with the cost learning, double marginalization will be even more. Without double marginalization, there is no need to contract. There is no need to coordinate. So now what happens is, manufacturer sets up the wholesale price and production quantity. And the retailer has two functions. Retail price will be a function of these two guys, and the ordering quantity will be a function of these two guys. This is the decision the manufacturer makes. This is the decision the retailer makes. Okay?
I don't understand. Because if they produce some quantity,
yeah,
and he doesn't buy all the quantity, what will they do with the ads?
So
they will equal somehow, I guess.
yeah, you can show that this will be equal, but if manufacturer can hold inventory, which will be carried over the next period, that's another problem. I don't have the time to do it, but the paper has both of them. Okay. So paper has the two issues here, but we do not deal with the retailer holding inventory. In fact, there is a paper that has never been finished. It's sitting still unfinished, and all thing is there, but it has not been finished. Where you can actually both can hold inventory. When retailer holds inventory, it's called strategic holding of inventory, because retailer then has a bargaining power. It has an inventory, so it can force the other guy to. So anyway, we're not getting into that. But the question is important. So you can see that one is, I'm not going to do that. It's in the paper. Hi, how are you? Yeah, we are now developing the model, so you are at the right time. So here's the notation. The first period is, this is not working anyway. It only works for this.
The concept doesn't work because this is a screen.
Yeah, but
So
it doesn't work here. It only works here. Yeah, fine, no problem. So 2 periods are I equal to 1 and 2. First period is interpreted as an infant stage. Second period is the mature stage of the industry.
Can use this.
Yeah, okay. Well, I cannot hold two of these things. I can just go like this. Excuse me. second piece called a mature stage. There are a number of people who worked on this problem, including Fudenberg and Tirol, Dasgupta and Stiglitz. There are a couple of Nobel laureates there already. And then there are some Portuguese people also worked on this problem. And so we are basically saying that this is OK. Now, we have a demand parameter, so we're going to assume a linear demand. So AI is the market potential, by which we mean that if the price is 0, that's what you're going to order. This is the maximum you'll order. And B is the price sensitivity. You can make it depend on I, but it just makes things more complicated. It doesn't add anything to the substance of the problem. PI is the retail price in period I, WI is the wholesale price in period I. Cost learning, we have a C1 is the production cost in period 1, which is given to us. The C2, which is a random variable, is the production cost in period 2. And C2, small c2, will be the realized production cost at the end of period 1, which will, of course, depend on how much you produce. Lambda is the random learning rate, which can go from 0 to some maximum number. Production variable will be the small qi is the retail's order quantity, and the big qi is the manufacturer's production quantity. And if I were to do the second part of the model, then there will be inventory. But that's not going to be covered in this talk. OK, sequence of events. Let's go through all of this. So manufacturer is a reader, retail is a follower. OK, 2-period learning curve. So we go like this. Everybody observes the state. The state is now C1. If the inventory were to also include it, then the state will be C1 and I1. There will be 2 state variables. Given that, manufacturer will announce W1 and a Q1, wholesale price in period 1 or production quantity in period 1. Given those, retailer will react and announce a reaction function, which will be P1 and Q1. So this would be that. Then infant stage finishes, learning takes place. When learning takes place, C2 is realized as C2, small c2. Everybody observes that. Everybody observes that. Then after they observe, manufacturer will decide W2 and Q2. And then these guys will decide, why there's one more. Yeah, this guy decides P2 and Q2. And then game is over. OK? So that's our setup. And it will be solved as a backward induction. So we're going to assume certain things. The demand is DI equal to AI minus BPI for each period. It's a linear, so demand is price dependent, which is unlike the news vendor problem, where the demand is random variable, not price dependent. Here, stochastic production cost learning, C2 will be C1 minus lambda times Q1, where lambda is a random variable. OK, so that's the learning rate. We assume lambda to be between 0 and gamma, where gamma is the maximum learning rate. Now, in general, you will need a distribution of lambda. But because of this problem, we see the only thing that appears in our calculation is going to be an explicit solution. The only thing that appears are mu and the standard deviation sigma. It is just a special class of problem where you don't need the whole distribution. Manufacturer may or may not have an option of inventory carryover. In our talk, we're not going to do that. Back orders are not allowed. That means if you don't solve it, the sales are lost. Manufacturer retail are forward looking. Stackelberg game, we're going to use the circle game. These are innocuous only because if you have them, then you do first order condition. If they are above or below, you have to set the boundary. You have to mean this and mean that. So I avoid all of that. So this is our model. Now, centralized solution is just a dynamic programming. So you solve that problem. Your dynamic programming, you solve that problem first in the second period, and then you solve the first period problem, and the total profit is pi. You see there's an expected value. There's a price times the mean of Q1 times D1 P1. So mean of those will be the sale. If the D1 P1 is lower than demand, you will sell it. If the D1 P1 is higher than demand, then only see Q1. So that would be the sale. So that would be your revenue. That would be your cost. In the second period, that would be a sale, that would be a revenue, and the C2 being a random variable, there's an expected value. And this is dynamic programming problem. We can solve the problem completely. So the P1 star is given by this formula, and the Q1, which is a function of C1, but C1 is given, so you don't, even if the C1 was not given, the problem can be solved that way. So you have a Q1 star, which will be A1 minus P1 star of C1, once you are given this one. And then you get to second period, you get that solution, you finally get the profit. So all of this is dynamic programming, and you can, now we solve the problem this way. So now the manufacturer retail dynamic problems are as follows. This is the manufacturer's output function, which will depend on everything, and expected value. Now notice now the revenue of the manufacturer is now W1 times small q1, because W1 is the wholesale price, the small q1 is the order quantity. That is the money coming from the retailer to the manufacturer. The cost will be the same. It will depend on capital Q1. In the period 2, it will be like that, and the C2, small, big C2 Q2, and the unexpected value. Retailer's profit, on the other hand, will be P1 min of this small q1, W1 q1 will be the cost. So the cost is now W1 q1, because that's what he's paying to the other guy. So the objective function in a decentralized setup is different than the objective function in the previous setup. And our state equation is C2, which is C1 minus lambda q1. C1 is given. And we can now solve this problem, and we're going to try to do that next. Any questions so far? There's no inventory right now. We are not allowed to carry inventory. That, I told you that is the second part of the paper, and I'm not going to cover that, because all it does is create one more state variable, and I create a little bit more complication, but nothing else changes. Yeah.
You can think of maybe perishable product, so that after when the period ends, so you salvage it, or it just it's perishable, so it has no value.
Well, I'm not getting into that because there are tons of models in this. My purpose here is to tell you that I can coordinate a 2-period supply chain, and that the coordination of a 2-period supply chain is not the same as the single-period supply chain. And I will also tell you that a 2-period supply chain coordination, the second period coordination is the same as what we know already, because the second period problem is a single-period problem. So that's the whole idea. And I will also tell you what is the Stackelberg equilibrium in this setting, and that I'm going to do in a multiple period. So this is the next slide where I'm trying to teach the community there. And so that's what I'm going to do. Okay. So here is something that we're going to spend some time. And the entire problem here is a notation. Once we have the notation, we can define what the Stackelberg solution is, okay, in a 2-period. So let's go slowly here. In a feedback Stackelberg equilibrium, the leader determines her strategy in a feedback form. So let x be the state variable and t be the time. Because remember, it's time consistent, so we have to solve the problem at any given time t. So you have x and a t, and a u is the control. So uxt is the leader solution given x and given t. The follower strategy is based on the leader's decision. So the follower decision will be the form v. He also observes x. He also observes t, but he also observes the u of x comma t. So that would be u x comma t for t 1 to n. Notice now, I am not asking you, because that would be a feedback form. I'm not putting that as a function here. Because if you put a function here, then it's a function of a function. It becomes a calculus of variation problem. That is not easy to solve. And for us, we don't need to do it because we'll coordinate the situation anyway. So that would be, so if the u was $1, that will be $1, not a function. Because you will observe the dollar, and you put that dollar into your reaction function, okay? And we'll say a little bit more about that. Okay, the leader strategy, I'm going to short form u. U will be ux1, ux2, all the way to uxn. N-period problem. This is u will give you the leader's strategy. The follower strategy, v will be v x1, then ux1, v x2, ux2, and so on down that. You can also put xi if you want to do that, but this is what we observe. Let u and v denote the space of strategies. This u and v, space of strategies of small u and a big small v. So, okay. And if you want to put some constraints on u and v, like u bigger than 0, you can do all of that. You can do all of that in defining these two guys. So now let's take a feasible solution the feasible solution, let's take any u in u and any v in v. Not optimal, but just any. If I take the any, I need to find out how the state is going to develop. Okay? So let's begin with that. The state is going to develop. This is a difference equation. And this comes from our paper in Siam control where we do it continuous time. But this idea is the same. So you have xi plus in period I is xi plus f of xi, ui, vi, lambda I going from t to n. And x of t is y. We have to have an initial value of x, which I given as y. Then, when you solve this equation for that u and that v, at any time t, at any time I, which is bigger than t, I will have a state variable x, which is this is the initial condition. So I need the initial condition, which is x of ty. Then this is the I, which is the period, and these are the uv, which are the decision. So I will denote that as a solution of that. Okay. Then I define the leader's objective function, which is going to depend on u and a v, and this can be written this way. And now let me go a little bit further on that. The colors are only to show you that where the parenthesis is open, where the parenthesis is closed. So we pi L will depend on the state observed at time I, right? We are now talking about I. I goes from t to n, right? We're starting the problem at t, and we have I that goes from t to n. So everybody observe the state, that's state. And it depends on the control. But the control depends on that state and that I, because that is your state, right? And it also depends on v of x, t, y, I, u, v, which is the followers problem. Then it depends on I, that depends on this closes here. So v depends on x, I, and a u. It closes here. And then depends on lambda I. So all of that closes from here to here, as we defined earlier. And then there's a salvage value and period, n plus 1. Same thing, we have a decision for the follower. The follower also has the same situation here, but the function is pi f versus pi l. And now we are ready to define. Lambda is the random variable. Learning rate. Yeah, it has to be realized. Yes. Function f. It's just a function of profit. Profit of the retailer and profit of the follower. It will be these guys. I'm giving a general setting now. The particular setting will be this one. So general setting, we have this, and now I define this. Notice, a pair of strategies u star in u and v star in v is called a feedback Stackelberg equilibrium if the following holds. I just want to mention here for the students as well, if you take a single person problem, then we define the maximum solution or optimal solution by one inequality. That means for u star, your profit is better than any other u, one inequality. When it comes to equilibrium, there is no such thing as optimum profit of anybody. All we can do is define an equilibrium. And the equilibrium is defined by two inequalities. So there's two inequalities in Nash as well as in Stackelberg. So these are the two inequalities. It says here, so u star and v star is our equilibrium quantity. And now what happens is that the guy leader is changing from a decision from u star to u. But when the decision is changed from u star to u, the other guy still keeps his response function. Remember? So v star is now going to operate on u, not on u star. And then for all u and u, for all initial condition y, for all initial t, 1 to n, the equilibrium profit is better than the profit that you get by deviating. Let's go to the other guy. Follower, the equilibrium is the same on this side, and now that guy changes his response function. But this guy still keeps u star, So response function then has an operator on u star for all v, all y, all t. This is the Stackelberg equilibrium on an n period problem. And this is slide 24. What is new here? Yes? I'm hard of hearing, so tell me.
In order for U star and V star to exist, so we don't need any further assumption on the space strategies, big U and V.
Well, these are U star and V star in those spaces that we already defined. We can define whichever way you want. I'm not worrying about measurability and existence, all of that right now, if that is your question. But I'm basically saying that those are the spaces that we define. U and V we can define on any given setting. Okay. So the slide 24 is the following. Stackelberg did not define an equilibrium. Stackelberg defined a solution. Well, the Stackelberg solution is such that for the second inequality, both V and U can change. It is true for both deviations. The inequality holds because the V is an optimal response function of U. And so that solution, that particular property cannot be generalized. So when you go from single period where the Stackelberg is not an equilibrium, it is not like a Nash, it is a stronger than equilibrium. That strong property of Stackelberg solution that he proposed in 1934 cannot be extended. That's the limitation. And so we are now following a Stackelberg equilibrium, whereas the single period problem, it is more than equilibrium. It is very, very subtle point, which only some people in game theory know, but most people think the Stackelberg is also an equilibrium.
So somehow, if I understand here, you have a game where there is one player moving first, and the second player is moving second.
Yeah.
And then this is one period of the game, and
Yeah.
you repeat this.
Right.
Okay?
Yeah.
So you repeat as an extensive form game, let's say.
So I think your question is direct to the next slide. So let me just go through that. So we solve this backward, okay? We solve the backward, and we get this table. So when we solve the backward, we get W1 star, we get Q1 star, we get Q1 star, which is a function of C1, W1, and Q1, because this is the wholesale price and a quantity, and we get the retail price. So we solve this backward. Once we solve it, we need to know how you operate this. So this is how you operate. You are in Sola's solution goes from 2 to 1. The implementation goes from 1 to 2. So how do you implement? Once you got the solution, how do you implement? So what you implement is this. You observe C1, and you have a table. So you look at the table, and you announce your wholesale price. And you have a table, and you announce your Q1. Once you announce C1 and once you announce W1 Q1, this guy knows W1 and Q1. He puts those guys in his table, he observes C1, and he gives you this. Then he also puts W1 Q1, and he gives you P1 star. And then when that happens, C2 star is realized, because C2 star is the C1 minus lambda of Q1 star. So it's realized, then everybody observes C2. And they look at a table. And they look at a table, they say W2, C2, they say, okay, it's $5. And then Q2 star C2, I'm producing 20 units. Then this guy finishes, and then those W2 and Q2, the decisions will come here, not as the functions, but the output of the function. And so this is how you operate this. So the game is solved backward and implementation forward. And once again, why feedback? Why open loop? And my own view is I do not know how to coordinate open loop. And maybe it's not possible, because after all, you are not taking into account the second, what is in the second. You don't take into account the realization of the demand. Okay, or the cost in this setting. So now I will do a revenue sharing contract. And buyback is equivalent. So let's do the revenue sharing contract. the contract will be defined as follows. C1, the contract will be defined as wholesale price as a function. Phi 1, W2, C2. Phi 1 is the portion of the revenue the retailer gets. Phi 2 is the portion of the revenue the retailer gets in period 2. And phi 1, phi 2 are between 0 and 1. This is the fraction. So this is going to be our contract. That means I have to define you these functions and these numbers. And if I can coordinate, which means I can get the same profit as the profit of the centralized problem, then I have coordinated. Okay, so this is what the next was. So subscript RS means revenue sharing. And the retailer's problem now is the following. He's going to decide the price between 0 and A1 because that 0 and Q1, Q1. And its profit is going to be phi 1, which is the portion of the revenue he gets. The revenue is P1 times Q1 dP1. That's the revenue. And the cost will be that one. And that's the revenue, and that's the cost. That's the retailer's problem. The state variable is this one. And the coordinating contract is as follows. For any phi 1, phi 2, which is also true, by the way, in a single period setting, they call it a flexible contract. That means any phi 1, phi 2 will coordinate the contract. All the phi 1, phi 2 does is how to split the extra profit. Because decentralized profit is here, the benchmark profit is here, so there's a margin, the profit, and how you split that profit depends on phi 1 and phi 2. But we don't care. We only care about coordination right now. Yeah, it depends on bargaining power. He can, if a manufacturer has a full bargaining power, he can give you 0 and takes all of it. Yeah.
So your trade point, let's say, for bargaining, is the decentralized profits. Each one should get at least his decentralized
No, they're good at least. That's a part of the contract. Yeah. Otherwise, you will not sign the contract. Okay. So you see, W1 is this. W2 is this. This is exactly the formula in a single period contract. So the second period is a single period contract, but the first period is totally different. It was never derived before. So that is a coordinating contract. You can show that under this contract, the profit is maximized. Yes?
I remember in the paper by Cachon and Larivière, so when they studied revenue sharing contract but in a static setting, they found that the wholesale price is negative.
What's the price? What?
Can be negative. That is the manufacturer.
Well, remember, first of all, their problem is different. Their problem is a news vendor problem, with the demand is stochastic. My problem is not that. My problem is the demand is deterministic. It depends on the price, but the cost is stochastic. Okay, so that finishes this, and then I will go to the next problem, which is another different variation of Stackelberg problem that.
So in this second part, when you do the sharing, you need to compute somehow the solution of the dynamic problem of decentralization in order to compute this one somehow, because it's your trade point.
I didn't.
To solve to construct your contract,
Yeah.
you need to solve the decentralized problem first.
Centralized problem is.
It gives you the minimum value each one should get.
Yeah.
And then for this one, do you also use dynamic here?
Yes. Yeah.
So dynamic programming.
Yeah. There are two ways to do it. One is that you compare the profit and then you solve some algebraic equations to get a contract. That's what's done in the literature. But once you get that, you need to show that it's a decentralized problem.
But there is some problem that may happen dynamically speaking, because if you imagine you do this many periods.
Yeah, it doesn't matter.
So from my trade point or my dynamic solution or my claim, I should, from this time on, what I should at every time on, I should get a profit.
Yeah, it is.
I should share.
Yeah.
So I should guarantee to each one.
Yeah.
At any time on that he gets his outside option, which is the profit he will get decentralized from that time on.
Yeah.
This should
Yeah.
be true for every time.
Yeah. Yeah.
So do you have this? Did you study this phenomenon?
Well, we only do 2 periods. We haven't gone to the multi-period problem yet, but the definition exists.
Because in the multi-period, you will the sharing you should do should be dynamically consistent. At every time period, you need to
Yeah.
more than.
Yeah, but that coordination here also happens that the same way. So you have a first period and a second period. Okay. So now I have another problem here. This is a paper that published in Siam Control, and it so happened one time that all the papers that I saw in the game theory Stackelberg setting was there was one leader and one follower. Or there may be a bunch of leaders and a bunch of followers, and the leader plays the Nash game, follower plays the Nash game, and there's a Stackelberg vertical component. But the thing is, why not the same guy could be a leader in some decision and a follower in another decision? That is a possibility. And the way I was wondering at one time, and I should mention that anyway, is that I grew up in a small village in India, and I watched the decision making by my parents. I was the 11th baby of my father, the last one. Yeah, I'm the 11th. I'm number 11. I am the baby. So the way it works is I've seen my sisters and my brothers getting married, and the decision, my father says, okay, mother, this is the money we have for this month, and my mother decides what to buy. Okay, so guess who's the leader here? Father is the leader. On the other hand, my mother says, okay, my sister is now 17-year-old or 16-year-old, whatever. Father, go find a man. So who's the leader here? Mother is the leader. The father then goes out and look for a man, and then somehow all this happens, and eventually they get married. So why not the same situation happen here? So initially, I approached Tamer Basar, and I wrote a paper with Tamer Basar and me. We wrote a paper, but we wrote a paper with open loop, because you can have an open loop mixed equilibrium. But we did not have the feedback, and later on, we also had an existence issue as well, but also under very limited conditions. So those 2 papers came earlier. Then we had a PhD student. So we, Ben Sousa and myself, the PhD student, we decided on working on the feedback, and we developed this idea. So we will get you this one. And the idea here is what is called a cooperative advertising. The cooperative advertising is prevalence in practice. So what happens, let me just give you a brief picture, because I don't know if we want to go into details of all of this. The cooperative advertising, so what happens is that in a situation where the retailer sells the goods, retailer can advertise, but maybe not enough. If it doesn't advertise enough, then the demand for the product that he's selling is going to be lower. So it hurts the manufacturer as well, because he's not selling much. So what manufacturer says, I will pay part of your advertising. That's called cooperative advertising. And if I pay part of advertising, then the retailer will advertise more. And if they advertise more, it benefits the manufacturer as well. And we can show that in many cases, that would be a better solution than zero subsistence. And so now what I'm going to do is I'm going to have a mixed leadership game of cooperative advertising, where the manufacturer also advertises. It's, you know, if you're old enough like me, there was an advertisement called Got Milk. So the dairy people are making an advertisement, or there was a General Motors called General Motors Mark of Excellence. It's a advertising by the manufacturer which sells the retailer to sell General Motors cars. So the question now is, why not retailer also subsidize manufacturers' advertising? So we wrote this paper, we sent it to marketing science. Marketing science says, where is the case We don't have any situation in practice where the retailer subsidizes the manufacturer, only the manufacturer. And we told them, we can show that if you restrict the retailer not to subsidize, then you lose. So the practice may be not very good. The practice should to change, but that's market. So we finally published this paper in Siam because the marketing science will not take it. So it was a participation rate, an arrangement whereby a manufacturer pays for some or all of the costs of local advertising undertaken by the retailer for the manufacturer's product is called participation rate, specify the percentage of advertising that the manufacturer will share with the retailer. There is a huge amount of money in cooperative advertising. As you see the estimate for 2007, I don't have current estimates, but these are marketing papers where a paper like 1987 paper that estimate 2000 was $25 billion for 2006 paper, so 1 year later. Here's some of the data that have marketing paper by Dutta et al. Or Dant and Berger. Industrial products, 69% subsistence rate. Consumer products, 74%. Consumer convenience product like milk, bread, toothpaste, 88%. So there's a huge amount of cooperative advertising going on in practice. So justification is done, and now we have papers here. There's a survey of cooperative advertising. You can sort of see IBM does 50% of advertising costs, Nature Bounty 50%, Apple 75%. The question is, no one in the marketing literature has ever asked the question, what is the optimal participation rate? So how do you settle that, right? You need to have a model, right? So we give you a mixed leadership game. When I first wrote the paper, I called them mixed leadership games. It turns out that the mixed leadership game is a special case of a multiple leader, multiple follower game. It's a special case because the same guy can be both places and it becomes a special case. So,
What is 70% of the media costs?
Advertising costs.
What does it mean?
It means that if the retailer spends $100 advertising, the Apple will pay you $75. It's called a participation rate. Okay, so there we have. Let me not get into all of that because there are some papers by.
Between Apple and is a contract. Apple say, okay, advertise, and they pay.
It's a contract. They say because otherwise the retailer doesn't advise and Apple suffers. So this is there are some papers here. I just want to mention that the earliest paper that we know for Stackelberg dynamic setting is Papavasipoulos and Cruz, 1979. It is, as I mentioned to you, it is absolutely inscrutable. It is impossible to read this paper, and you spend a lot of time to figure out what's going on. And so we finally generalized that to stochastic setting and also explained that. We sent the paper back to Papavasipoulos. He said, great, that finally somebody can read my paper. He was very happy. Then there's a Basar and Huri. There are papers on this field. I'm not going to get into the literature anymore. And this is the paper that I'm presenting today, which is the 2009 paper. Okay, so let me get into the game. So we have a manufacturer and we have a retailer. The manufacturer gives the percentage that will support the retailer. The retailer gives the percentage of advertising that he will support the manufacturer. So both people are announcing their participation rates. So that is the leading decision, right? They are both leaders when they decide the participation rate. Given their participation rate, both decides how much advertising they're going to make. So retailer will make that much advertising, manufacturer will make that much advertising. Okay, and so the Stackelberg game will be played like this. First, you will solve the reaction function, and then the Stackelberg component they will show. Each one of them will be a Nash game. So the horizontal game is a Nash game, and the vertical is a Stackelberg game. Okay, that's kind of the game, the situation here. Okay. The state at time is xt, market the state at the time xt.
Why you call it Stackelberg? Just because there are two parts, or because they
You can call it Stackelberg Nash. You can also call it Stackelberg Nash.
so to understand the timing. So at every time t in continuous time,
Yeah.
there are two periods.
Yeah. No, this is continuous time now.
Yeah, we're in continuous time, but at every time in the continuous time,
Yeah.
at every moment, let's
Yeah.
say, there are two decisions.
4 decisions. 2 participating decisions and 2 advertising decisions.
Okay.
So this is the percentage. This is 5%, this is 10%, this is,
So if M chooses 5%, what does it mean? 5%.
it means that the rate at which the advertising is done at that time t, the 5% of the advertising cost will come. You will see the objective function. You will see the objective function. It'll clear better once you get the objective function. So I'm now using, for the advertising sales dynamics, I'm using what is called a model that I put forward in 1983. It's called a Sethi advertising model. It has exists in Wikipedia. It has many, many papers. And as I speak, we have a paper in marketing and management science that is currently under revision. And the last paper I published was in operations research on generalization of the Sethi model. So this is the Sethi model. The Sethi model goes like this. XT is the market share. The total market is 1. Okay? So the market share, so the advertising by these two guys, VR, VM, these are the actual advertising dollars. It operates on people who are not buying the product. X is the market share, which means I capture the X% of the market. 1 minus X is the people who are not buying my product, and I'm asking them to buy my product. Okay, so this is the Sethi model here, and the delta X is attrition rate. People who are buying my product are also going to the other products. We are not modeling that as a game, but they are going. There's the attrition rate. They are going. They're forgetting advertising, whatever. So this is the model. By the way, there's an empirical justification of the Sethi model by a couple of people in marketing. So I'm not getting into all of that. And then there's a Brownian motion. So it's a stochastic differential equation. And that's how we develop the state evolution. And now comes your question. So manufacturer's objective function, discounted value, margin of manufacturer for every sale is M. So that is his profit. And when you make, that's by the way is called effort. So the effort has a dollar value. The dollar value is quadratic here. So the manufacturer will pay dollar amount of retailer at that percentage. On the other hand, when he advertises, he gets a UR percentage. So his cost is 1 minus UR times that. You see how the participation works? Similarly, for the retailer, the margin for the retailer is R times X, and he receives UM from the manufacturer, so he only pays 1 minus UM times VR squared. VR squared is dollar value of the advertising, and vice versa. When he spends that money, for the manufacturer's advertising. So we solved this problem. So this is our game.
The parameters are A, B, delta.
Parameters are A, B, delta, and a sigma.
And UM and UR are the decisions.
UR, VM, VR are 4 decision variables in a Stackelberg setting. So the UM and UR will be decided by, so what you do is you start from the backward. So first you decide VR and VM given UM and UR. But there are 2 people, so they have to decide a Nash equilibrium. Okay? So this level, so given UM and UR, the 2 guys are solved for VR and VM according to Nash.
So when you say differential game, so meaning that my decision at time t should depend on all the past somehow, for both players. The decision they do at moment t should depend on the past. Up to moment
It's a feedback situation. So it depends on past, but in this case, it's yeah.
But in your case, perhaps since you have this discounted, and perhaps you have a solution that is stationary in a sense, or depend only on the current state, and that's it?
Well, it's a Markovian situation. So even if you took the history, yeah. I mean, it's only Brownian motion here, so there's nothing going on, nothing more complicated. So what happens here is, as you know, the game is played at the Hamiltonian level at each instant. So just like in Pointryagin optimal control, you have a maximum principle, you have an adjoint variable, and once you have the adjoint variable, you can myopically optimize at every instant in time. And that is called the Hamiltonian maximization. So maximum principle says that given the adjoint variable, you can solve the problem as each instant in time by maximizing Hamiltonian myopically. Because you can do myopically because lambda takes care, the adjoint variable takes care of it. Similar situation happens here. So we're going to define a PM and a PR are the adjoint variables, okay? And given those adjoint variables, you will see that adjoint variables are multiplied by the state equation. You know, that's how you do the adjoint equation. So that's a state equation. So now we have a Hamiltonian with the objective function right there, and then PM, which is the adjoint variable, and the dynamics. And we will have the HR, which is the Hamiltonian over the retailer. And again, there's a PR, and so forth. That. So those given UR, you solve for VR. Leading decision are participation rates. Given those, you solve for VR by solving a Nash equilibrium on the Hamiltonian. Okay? So when you do that, you maximize the Hamiltonian. You take the derivative. You take the derivative with respect to VM and VR, and you get VM equal to this and VR equal to this. So that's your reaction function. That reaction function, you take it upstairs. So we take the reaction function upstairs, and we now have a Hamiltonian for the manufacturer and the retailer, and I take the reaction function upstairs, and I solve for UM and UR. Okay? So I solve for UM and UR, and then we go and we define the PM and the PR are just the derivative of the value function. That's VM prime and VR prime. So we put that guys into there, and we have what is called a Hamilton-Jacobi-Bellman equation. The Hamilton-Jacobi-Bellman equation gives you the solution to UM and UR in terms of VM and V prime, and you get then VM and VR. And the Sethi model has a single property that is why it is going over all the time, is because the value function can be assumed to be linear. Now, when I say assumed to be linear, it means I can solve the for value function completely, and I have a verification theorem that says it is an equilibrium. But I cannot tell you that it's a unique equilibrium. I can only tell you it is an equilibrium. In a single period, single agent people, uniqueness is simple. Your profit is maximized, you're unique. In a game, you can have more than one equilibria, right? And we do not know where the other equilibria is, if there is any. Nobody has solved it, because once we have the value function which is nonlinear, then the second derivative of the value function will come in. Remember, the second derivative of the value function doesn't happen in the linear value function. So if you assume linear value function, the equations are like this. So we solve that problem, and we assume the value function to be linear, 4 parameters, and we put that into the HJB equation, and we compare the coefficients, and we get 4 algebraic equations. We need 4 parameters, 4 algebraic equations, we solve it. And of course, algebraic equations are about the best we can do. After that, we solve them somehow or the other. Algebraic equations are easy to solve, or sometimes there is no closed form solution for them. Even single equation, I can give you an equation that has no closed form solution, but we can solve it by numerical means. Okay?
There are solutions. There are linear solutions in your case.
No, we proved the existence and everything. It's not a problem there. We prove existence because we need beta. We need something to be positive. It's not like something that we can just solve for any value. Because when you solve that, you will going to get certain cases. So there are cases here. Okay. So first case is this one, and we find that in this case, manufacturer will not give you any subsidy. Only the retailer will subsidize. Then we get this case where we can show that both are guys are subsidized. And we can do a priori these, so we can find out what these are. And then we have the third case where we see the retailer is not going to subsidize, on the manufacturer will subsidize. So we solve these equations. We solve these numerically in the paper for a slightly more general problem, because we also wrote a paper in Automatica where we also said that the influence on this depends on that, that, and that. This also continues to solve the value function as linear. So for our numerical analysis, we use this particular model, where there's a synergy which is k bigger than 0. And so here are some numerical solutions for this, and I want to show you what that is. So as Rita said, parameters, retailer's margin is 1, A and B are equal to 1, K equal to 1, delta is 0.1, the discount rate is 0.05. So these are the parameters, and for which you see what happens. Here's a margin of the, here's the margin of the impact of the manufacturer's margin M on part. So here's the margin for the manufacturer. And here is subsidies by the retailer, here's the subsidies by the manufacturer. Look at what happens. When manufacturer's margin is low and retailer's margin is high, then retailer will advertise on his own accord. Because his margin is high, he's not going to advertise less. So if he's going to advertise on his own, why should manufacturer give him a subsidy? So until this time, the manufacturer's subsidy is 0. But after manufacturer becomes higher margin, its subsidy goes down. Its subsidy goes up. On the other hand, the retailer behaves the same way. When the manufacturer margin is low and the retailer is high, retailer is going to subsidize the manufacturer. When the other way around, the retailer is not going to subsidize the manufacturer. And clearly, the money is being transferred from one guy to the other. So if $10 is transferred to this guy and $5 is transferred to this guy, the net transfer is $5. So we have another graph where we give you a net transfer. So you see here, this is where both are 0. This is where one guy is 0 and one other guy is 0. And this is the net transfer. So this is the net transfer of impact of margin on net transfer from manufacturer to retailer. So we give you these things for this. And then we conclude the paper. So difference between Nash and Stackelberg game, we showed you that. We also give you a type of Stackelberg equilibrium, 2-period supply chains. By the way, there are more than 2 equilibria possible. And there are closed loop and all that. And we have a Siam paper in which we define many of the equilibria. Depends on the information structure, as in Basar Olsuk book as well. So definition of multi-period feedback, dynamic pricing, production and supply chain with cost learning, revenue sharing contract with coordinate the 2-period supply chain, mixed leadership game of cooperative advertising. We do not coordinate that. We do not have a coordinating contract for this. But we only can show that cooperative advertising is better than no cooperative, or we give the optimal cooperative advertising. So you can see, if you can see that in that particular situation, we told the marketing science people that if we turn off the UR to be 0, then supply chain will be suffering. So why not? Why not subsidize? But you know how our field requires a lot of empirical data, and if you don't have something, they sometimes don't publish it. Okay, so mixed leadership, and there are some more papers now, but these are some of the papers that I have listed in this talk. That one is a paper survey that we wrote. There is a paper in POM that gives you the cooperative advertising that I published. I tell you, Basan and Ben Susan and Sethi wrote a paper on mixed leadership for open loop solution in 2010. Then we wrote a linear quadratic differential game with mixed leadership in 2013. There's a Basar Olser book, Ben Susan Chen and Sethi. This is the paper I presented today. Oh no, this is not this is the global solution of stochastic different game. I didn't do that. I presented this one. This is where I have many different equilibria definitions, and this is a channel coordination paper. So. There are many other papers in this field, but I'm just not going to. So I'm kind of done here.
Questions.
Thank you for the presentation. So I have a question about the first model. So can we see the first model as a Cauchy problem, so we can make it easier to show the existence of U and V?
Well,
under some assumption on F, like linearity on X or something like that.
What you're trying to say is that in the first model, you would like to generalize it. Is that what you're going to try to say?
In continuous time.
Generalize and then show the existence of a solution?
The model is like a Cauchy problem.
Model is what?
Is the model like a Cauchy problem? That was the question. Cauchy.
Cauchy. No. This is. We don't get into business. This is you can solve the problem completely anyway, completely explicitly. But what I suggest is to generalize that into more than two periods. That's a better way to go than going to generalizing the problem, because our field is not going to be interested in that. Okay, I mean, that's sort of what I would say. Because in the end, you need in order to coordinate a supply chain, you need a supply chain problem. Yeah. Yes?
Thank you, Suresh. I have two questions. The first one is about the last presentation you made.
Yeah.
I was actually a bit confused about the word cooperative marketing. I mean, the first level is when you have the manufacturer paying a percentage of that advertising cost, assuming that the advertising will end up with the sales.
Yeah, that is
so
the
let's
equation.
assume that.
Yeah.
And then there is a second level where you spoke about mixed, where the manufacturer gives a portion, but also, which is less traditional, the retailer also gives a portion into the advertising of the manufacturer.
Yes.
But when I looked at the equation, I think it's page
Let's go back.
slide 41, I believe. I saw that for some reason I saw that the functions are here.
Here?
Just
Here?
next.
Next, that one?
You see here? So you see, I just noticed that the functions are somewhat completely separable. I don't know whether, so I just wanted to see, just a naive question, whether you asked if we just look at the single, not the mixed game, where basically you have the retailer that advertises with VR, and then the manufacturer gives a UM. Is the equilibrium going to be different than
it's going to be different. If you said u are equal to 0, if you said u are equal to 0 to begin with, then it's a standard problem.
Yes,
Yeah,
but I just couldn't see in what, I mean, how does the interaction between both?
The interaction between them coming right here, for example, if you look at the UM and UR, given UM and UR, I'm going to advertise
VM
everybody.
and VR.
So given UM and UR, you're going to take the derivative of that guy with respect to VR and derivative of that is with the VM. When you take the derivative, you get these two equations where you get VM equal to this minus UR and VR equal to this minus UR. That's where you get this. Now, in this particular problem, you don't get UR-UM here and UR-UM here. It's a simple model. So here you don't have VM as a function of UR-UM.
Yeah.
In general, you can have a VM as a function of UR and UM.
Yeah. So
but that it would require another problem.
Are we assuming it's a single? There must be something. I mean, I understand since it's if it was the functions were completely linear at the Hamiltonian level. I mean, you could have completely separable, and so you have some level of total revenue that is going to be affecting. But my point is, like, physically. If it's, are they selling the same product, or are they? What is really?
There's only one product that the manufacturer is selling through the retailer. Now, retailer may sell other manufacturer's product, but that is not part of this game.
Yeah,
you're right.
But also the manufacturer advertises for that same product.
Yes. Yes. So
in a sense, they are somewhat sharing the market share. I mean, they are competitors in the market share. You see
but the way the retailer influences are different.
I understand.
Because the retailer knows the local market.
Yeah.
So it can direct the advertising more efficiently in some sense, whereas the other guy is a global guy.
Yeah.
And so
because there was a sentence in when you defined, I know I missed it. You went too fast because you said at the national level and then at the local level. Yes. You saw that in the when you introduced.
Sure.
Here.
So there is advertise. All we can tell you. Remember now, this paper was not expected by marketing science. Some of the objections that you raised may be very similar. But there is a national advertising that you knew. There was an advertisement by General Motors saying, General Motors mark of excellence.
Yeah.
And every retailer, you can have, see the thing is this. This can be generalized to this can be generalized to one manufacturer and multiple retailers, which is no problem. So we have a multiple retailer game and multiple in the JEDC paper we have that. So you can generalize that to multiple retailer and it will be a little bit easier to solve. So each retailer is going to subsidize the manufacturer. The manufacturer now has, let's say, 10 retailers in 10 different states in the United States, and manufacturer is globally advertising in every state, where the retailer is advertising only in their state. You see what I'm saying? That would be a more interesting problem. And will satisfy your objection. But
I think so. I think definitely something that would make sense is, for example, if you have your own manufacturer and you have some retailers, like some shops online or whatever, that belong to him, to the same company. And then you have retailers that are outside of the company. And you want to decide this policy,
you can. Our purpose was to demonstrate that there is something called a mixed leadership. That was the. You can generalize this problem to make it more realistic, and I think that you are right. If you take the manufacturer selling just with one retailer, the problem is a little bit limited. But it's easy to say there's one manufacturer who sells entire United States or all Morocco, and then there are different retailers selling that product in different states. So these retailers are now going to, and you can assume that these retailers don't compete with each other because they're in different states. That make it simpler. But if they want to compete, again, the problem becomes more difficult. But multiple retailer will still go through linear value function, because we know we have solved that problem in another setting. So you can have UR1, UR2, UR3, all subsidizing the manufacturer. The manufacturer objective function will be where are the objective function here? So there will be 1 minus UR1, UR2, UR3, something like that. Okay.
I think the retailers, they compete customers they would get the products from the cheaper retailer.
Well, you can have more than one retailer in each state. You can have a more than retailer in your neighborhood.
Yeah.
Then they will compete.
Yeah, but that's maybe a third level
Yeah,
of.
Yeah, there are many generalization possible.
Yeah.
You need a bunch of army of students to do that.
Yeah, yeah.
We cannot do everything.
So
But I think that, yes, absolutely. I suggest you guys to go into a maybe 3-period problem to begin with. And these papers are possible to publish in our journals. But if you want to prove existence and Cauchy problem, forget our journals. You will have to find another journal for that.
yeah. So the other problem was very interesting. I mean, especially with the learning, with whatever is happening with technology diffusion and like renewable energy. I mean, this could be in electrical type. The learning. I was speaking about the first one, where you have
this is the first one.
the gamma. Yeah.
So, but there are many supply chain problems in our literature. I just took one.
Yeah.
And you can look at another one to see what happens in the 2-period. And the only thing right now is that the supply chain coordination was a raise in supply chain management about maybe 15 years ago. And now everybody is now doing machine learning, they're doing AI. Supply chain coordination is now on the back burner.
That is true.
So fashions come and go, and right now if you look at I haven't sent you that article, but I moved to Texas in 1997 when I was the only operations management professor and there was no PhD program. So I started a PhD program and hiring people. We were nowhere. We were 150 ranked in research according to UTD. We are now #1 in operations management. We have 25 tenure track faculty members, 16 non-tenure track faculty members. It all began with one. So I finally wrote a paper I will send you. I forgot to send that. I will send. I'll send.
So
I presented that paper in Taiwan.
Okay.
Yeah. So
no, but I agree with supply chain because it's just. But operations will always stay. I think that's that's going to continue. I believe. Maybe supply chain. Yes, I agree. It was at a certain point a move.
Yeah.
But it is having its limitations as we go. But I just wanted to, when we read the sequence of the events, they do make sense. However, let's forget the revenue sharing, because I think you added the revenue sharing at this such sharing. That we split.
We do the revenue sharing here.
Yeah.
Here.
Yeah. So when we do revenue sharing, when demand is random.
Here the cost is random.
I understand.
So let me give you some history on that. So we did not look at revenue sharing in the news vendor problem, the random demand, because I thought that world must have looked at it
for a
long time
ways,
and they didn't.
Yes.
And then what happens is that my student who is working on this is a lazy guy, and it takes long time to do this. In the meantime, there is a paper by two Koreans. And they published a paper in EJOR, I think, of the news vendor problem with the random demand, with the 2-period. Yeah. The problem is they don't have a definition of Stackelberg equilibrium. They don't know what it is. They don't talk about it. B, they make some minor mistakes which can be corrected. But somehow or the other, they don't have the idea of a feedback in a way that we know. So in our paper, we do talk about that paper a little bit, and we do mention that with the correction, their solution is correct in some way, but it is not an explicit solution of
Yeah.
any kind.
Yeah.
So I think we did not have the time to go back to that again and redo it, but
Yeah,
yes, there is some effort on that.
Yeah,
That-
but I just wanted to say, when we speak about revenue sharing from a demand perspective,
Yeah.
because we don't want the retailer to take the risk on its own, so the order quantities will be lower. So we want to share such that we raise the revenue and hopefully have something extra to share. But what I see here, when you have the cost that is random,
Yeah.
I feel that the mechanism of revenue sharing is not the same.
Maybe not, but it coordinates.
Well, I just
It
because when you have the first period demand
Yeah.
that is fixed, right?
Right?
And let's say we observe in the second period
Yes.
that learning, you know, the gamma, such
Yeah.
that we
Or the C2 or C2.
yes,
Same. Yeah.
C2. The whole risk can be absorbed by fixing the P2.
Fixing P2.
P2. When you fix P2 and then D2
Yeah.
is-
Okay.
You see my point?
No, I see your point, but I can tell you the following.
Okay.
You can fix the P2, but you're going to fix it by fiat.
Bye.
By fiat. You point a gun to the retailer and say, that's your P2.
Yes.
But that's not decentralization.
Okay.
We are now
You-
so I often talk about the people. I said the supply chain coordination. There's a one way to supply chain coordination. The manufacturer points a gun to the retailer and say, do this.
Yeah.
And of course, I will give you some extra money
Yeah.
if you do that. But it is not a decentralized setting. It is a by fiat. What you need is a decentralized mechanism.
I don't know what
Fiat means I order you to do so.
Okay.
But I order to you by pointing a gun at you, let's say.
But this is a leader. You say it's a Anyway, something I just
Yeah.
wrong because it's just a first intuition. But I just saw that like when it is a demand and it's volume times the price, and I am able to share that volume, I understand the meaning of sharing the risk, and then of course
The risk exists here as well.
Yeah.
The risk exists here. Because if you don't order enough,
somewhat diluted in
Yeah,
the second price decision, because we take all that effect and we inject it in the P2 in the by the manufacturer.
well, not just P2, this
Really-
both P1 and P2.
at the
It's not
first,
just, yeah,
periods,
of course,
I mean, in the
both of them.
response.
Both of them will change.
Yeah.
Because if you see here, if you look at the P1 in the centralized setting, here's your P1 and here's your P2. Okay? If you look at the decentralized setting, here's your P1 and here's your P2.
So where is P1?
P1 is here. It's a function of C1 and the announcement of the manufacturer.
Okay, and where is gamma in all that?
Gamma is because you came later. So now I'm giving you a talk again. Okay?
No.
No problem. Gamma is a random variable that decides the learning.
Reason in C2.
More you produce, more you learn. But how much you learn depends on the random variable.
Okay.
And the gamma is between 0 and gamma. So you will realize that. So there's a risk.
Implicit, yeah.
Yeah. No, I wasn't going to have a non-stochastic problem. Otherwise, people will say, okay, it's a deterministic problem. No. There's a risk here. Yeah. Yes.
Okay, thank you.
No problem. But it's a good question.
So, last question, okay?
So in the introduction, you criticized the full commitment because it's difficult to enforce. So how about enforcement of revenue sharing in practice?
Revenue sharing is not done in asymmetric information. We are now talking about asymmetric information where the information is not same. Right now, so there are model of everybody has the full information. That is one. Then there's a partial observation model, but everybody knows what the partial observation, everybody has the same information. So the sigma algebra of different guys are different. Here, this is the same. Everybody's underlying sigma algebra is same for everybody. And so there what happens when you have asymmetric information, Meyerson came up with the idea that of all the possible contracts, you can limit yourself to only truth-telling contracts.
Revelation principle.
But that's only good for single period or single period type problems. When you have multiple period problem, that thing breaks down. So my own view is the world is dynamic, not static. Okay? And I mentioned there was an agreement between Putin and the West, and Putin took Crimea, right? Because commitment, what good is commitment? The commitment is only good if Americans started fighting with Putin and he goes back. But they didn't do it. Yeah. So full commitment is a magic. It's a fool's paradise. There's no such thing in the world. There's no such thing as full commitment. Look what happens everywhere, right?
So I think we're going to stop, and we're going to thank Professor Sethi for his presentation.
Thank you for listening, and thank you for spirited conversation.